Hi, everyone, and welcome back for section 3 of Factorial ANOVAs here in Psych 3530. This section is going to be on what we call marginal means. We'll get into precisely what those marginal means are later, as well as looking at ANOVA tables. So the last two sections have really been just sort of general background information on factorial designs. What are they? Why would we want to use them? Why do we need them? How do we talk about them? How are they organized? And then what types of effects do they produce? In this section, we will move forward into discussing more statistics relevant issues with a factorial design. Meaning we're going to talk about starting to make real decisions from a statistical test about interpreting both these main effects and interactions. So we're going to start with what are called means tables and marginal means. And then we're going to look at actual statistical significance testing with ANOVA tables and talk about how we're going to use these two things together in order to understand where our effects are found in any particular factorial ANOVA. So let's just keep it simple and have an example with a 2x2 design. And let's imagine that we want to understand the impact of alcohol. So whether you have drank alcohol or not, we have a drunk group and a placebo group down here, versus, the effect of alcohol on shock intensity, which is going to be a measurement of aggression. So if you remember the Stanley Milgram experiment where participants had to make decisions about shocking another person, this is kind of like that. This is what they're proposing, is that a measurement of aggression might be how much would you shock someone if you're given the opportunity? Would you just give them a light buzz of a 1, or would you really try and hurt them with a 10? So that's going to be our proxy for aggression, since it's not really ethical to measure oftentimes real aggression, such as how many times would you punch this person in the face given the opportunity. We clearly can't do that experiment, so we have to come up with something sort of fake that we can do. So we want to understand the effect of drinking on aggression, measured as shock intensity. But we think that drinking might also be impacted by body weight, that there might be something going on with an interaction between how much you drink and your body weight, both interacting to produce your aggression of shock intensity. So we want to include both of these variables. We define our levels for body weight as men who are light, who are around 150 pounds, versus men who are heavy, who are around 215 pounds. And then we have a manipulated independent variable. We have a group that we intentionally get drunk. Yes, that can actually be done ethically. There are some wonderful labs around the country and the world that study the effects of alcohol on all kinds of different cognitive and physical processes. It is possible to actually ethically get some people drunk and then study the effect of that. And then we have a placebo group. This is a group that gets a drink, but it actually doesn't have any alcohol in it, but they don't know that. So this group is the 13-year-old version of yourself who is acting like they're getting drunk even though they're not, if we all remember back to doing that. So we have a 2x2 factorial ANOVA, which gives us 4 experimental groups: light men who do not drink, light men who do drink, heavy men who do not drink, heavy men who do drink. And these numbers here in our little, what I'm going to call a Punnett square, for lack of a better term, these little numbers in each of our cells represents the average score of the participants that belong in that cell. So maybe we have 25 participants in each of these cells. So we have 25 light men in the placebo group, and their average shock intensity that they chose was 5.09, right? Our measurement of aggression. Maybe we have 25 more light men in the drunk group. They averaged a 6 on aggression. We have 25 heavy men in the placebo group who averaged 4.72, and 25 heavy men in the drunk group that average 7.19. So we can use this table to help us try and figure out whether we have either main effect of body weight or drinking, and potentially an interaction of the two. So what we're going to do is we're going to step through sort of arithmetically and mathematically what we would have to do to consider each main effect and then consider the interaction. There's going to be no real difficult math involved, nothing beyond averaging and subtraction here. So we need to calculate what are known as marginal means. We call them marginal means because they end up in the margins, as you can see, the bottom and the right-hand side of this table. Our marginal means help us reveal whether or not there is a main effect of either IV. Now, if you remember back, I believe it was to section 2, we discussed how main effects are essentially the effect of a single variable while averaging across the other variable. And so that's exactly what we're going to do. So let's take body weight, our first independent variable here in green. If we want to try and assess the main effect of body weight, what we need to do is we need to take all light men, right? And all light men means anyone under here in the table. We need to take all light men and average their scores. So we're going to take 5.09 plus 6.00 divided by 2 gives me a light man average of 5.55 on aggression. Now, look, we're literally averaging across independent variable number 2, which is drinking, right? So we take all the light men, we average across, and this 5.55 represents all light men regardless of drinking condition, right? Not considering the drinking condition because we've averaged the two levels of drinking condition together. We do the same thing for heavy men. We take 4.72. We average it with 7.19. So we add them together, divide by 2, and we get an average heavy male aggression of 5.96, regardless of their drinking condition. So if we want to assess the presence of a main effect of body weight, we compare these two numbers, 5.55 and 5.96, because 5.55 is light men regardless of drinking condition. 5.96 is heavy men regardless of drinking condition. And so that's the exact question we want to answer if we're interested in the main effect of body weight, which is there an effect of body weight regardless of drinking condition, right? Not considering drinking condition. We do the same thing across the other direction if we want to evaluate the main effect of drinking condition regardless of body weight. So we take all the placebo people, the not drunk people, whether they're a light male or a heavy male, we average them together to get 4.91. And we do the same thing for all of our drunk men, regardless of body weight, we average them together to get 6.60. And then we want compare these two numbers right here, 4.91 and 6.60, to assess whether we have a main effect of drinking condition. So I want you to take a minute, maybe pause the video, or this might not take too long. So maybe don't pause the video. I'll just kind of go silent for 10 or 15 seconds. I want you to consider whether there is a main effect of body weight, meaning compare these two numbers, whether there's a main effect of drinking condition, compare these two numbers, and then see if you can come up with like a little mini eyeball interpretation of how you would describe each of these effects. So go ahead, I'll go silent for about 15 seconds. Okay, so let's consider body weight. Now, heavy men, it looks like on average, are slightly more aggressive than light men, right? They are higher. 5.96 is a larger number than 5.55. But we also want to consider the scale of our outcome, our dependent variable. This is a 1 to 10 scale. On a 1 to 10 scale, we have a difference of 0.41. So almost half a point. It's something, right? It's not nothing. It's something, but it's not enormous. It's not dramatic. So, yeah, maybe there's a main effect here. What we're going to see later in the lecture is that to decide to parse out whether this is a real main effect or not, we need a statistical test, right? This one is not very obvious. It looks like there is, but maybe we're not super confident in it. So we need an ANOVA. We need an F value with a P value to make a decision about statistical significance. So I would categorize this as like yes, but maybe. And then we look at the main effect of drinking condition. The non-drunk placebo group scored a 4.91 on aggression, and the drunk group scored a 6.60 on aggression. This one looks pretty obvious, right? On a scale of 1 to 10, a difference of, what is that, like 1.69? Yeah, I think my math is right there. We have a difference of 1.69 on a 10-point scale. That's a pretty substantial difference. So it looks like we're pretty confident that we have a main effect of drinking. So maybe heavy men are more aggressive than light men. Yes, but maybe. And I think we can say like definitely drunk men are more aggressive than non-drunk men, right? We're really confident in that one. So this discussion of scale is also really important. If the scale of shock intensity was 1 to 100, then these differences would both be trivial and we wouldn't care about them, right? They would represent nothing because the scale is so large and the differences are so small. But on a smaller scale of 1 to 10, the drinking condition difference looks fairly large and the body weight difference looks plausible, like it looks moderate. So we always want to consider this issue of the scale of our dependent variable. So we also want to keep in mind that, again, we're just kind of eyeballing the numbers. We're just trying to understand sort of the nature of the relationship, right, between the different conditions and their different averages and how this all kind of works together. We're not yet able to really make any direct decisions about statistical significance. We're just trying to eyeball the effects to get an idea about them. So we would have to run what's known as a factorial ANOVA. Remember, we just finished one-way and repeated measures ANOVAs, which will give us an F-test statistic for the main effects. So we would have to actually run the stats to know for sure whether the effects are significant. But we can kind of eyeball them and start to interpret them from the marginal means. So, yeah, it looks like the men in the drunk condition are certainly more aggressive than the men in the placebo condition. And the heavy men are more aggressive than the light men, regardless of whether or not they drank. But we might want to qualify this body weight interpretation to say that, that difference was relatively moderate. So we might expect the effect of drinking to be statistically significant, and the effect of body weight might kind of be up in the air for us, and we would need to really do the statistics to confirm or deny that difference. So now that we've looked at how to establish or how to eyeball our main effects, we want to look at our interaction. So remember, the interaction is this third emergent effect, which is essentially, does the effect of drinking on aggression depend upon body weight? So does the presence of alcohol change light men's aggression differently than it changes heavy men's aggression. Or again, put in a different way, are light men and heavy men differentially impacted by alcohol? Does the effect of alcohol depend upon your weight? So let's take a look at how we would do that. Using this means table, we don't want to find means for our interaction. We want to find difference scores. So difference scores is going to mean subtraction. Now, we only want to do this one direction. It doesn't matter if you go left to right or top to bottom. I say just go top to bottom. It literally doesn't matter. So make it easy on yourself and always just subtract these means down the table. So 5.09 minus 6 gives us negative 0.91. 4.72 minus 7.19 gives us negative 2.47. So we have our difference scores. And now the question we want to ask is there a difference between our difference scores? So do our difference scores differ from each other? So let's look at light men. Light men who did not drink averaged an aggression score of 5.09. And we can ask ourselves, well, how did drinking change their aggression? Well, it increased it by 0.91, right? They went from 5.09 to 6. This number is negative because when you subtract a smaller number, or a bigger number from a smaller number, you get negative. But what's happening is that the light men become a little more aggressive when they drink, right? 0.91. What happens to the heavy men? When the heavy men drink, their aggression score changes a lot, 4.72 to 7.19, meaning they increase their aggression scores of 2.47. So what we see happening looks like an interaction because our difference scores differ, meaning the impact of alcohol on light men is pretty small, 0.91. But the impact of alcohol on heavy men is dramatic, right? Alcohol treats light men differently than heavy men. The effect of alcohol depends upon whether you are light or heavy. Light men see a moderate, maybe small to moderate increase in aggression. Heavy men see a dramatic, large increase in aggression. So, this variable, drinking, is treating men differently based upon their body weight, right? It depends upon your body weight. That key phrase is our marker of an interaction. So, again, a difference between our difference scores suggests that we have an interaction. So, does the effect of drinking on aggression depend upon body weight? It appears so. We can say this both ways, right? The drunk group was more aggressive than the placebo group, especially for heavy men, or the effect of drinking on aggression is greater for those with greater body weight, heavy men, than those with lower body weight, right? Doesn't matter which sort of emphasis we put on which variable, the interaction is interpretable either direction, either way. So, with our means tables and our marginal means, we can get an idea about the effect of our variables, both the main effects and the interaction. But we have not yet established statistical significance. For that, we need a statistical test. The statistical test that we use for factorial ANOVAs, or for factorial designs, is a factorial ANOVA. This factorial ANOVA is going to allow us to examine statistical significance, and it's going to give us an F value for each of our main effects and an F value for each of our interactions that we can interpret in the same way that we've been interpreting all of our other statistical tests. So there's a lot going on here. Let me break it down. This is sort of a general ANOVA table. It probably looks a little familiar to your one-way or repeated measures ANOVA tables, in that the purpose of an ANOVA is to break down sources of variance, right? ANOVA literally stands for analysis of variance. So what's going to happen is that we get in a 2x2 design, we will get 3 relevant F statistics. We will get a main effect for columns. That's the variable that was in our columns. That's was body weight in our last example. We will get a main effect F value for the variable that was in our rows. That was drinking condition. And then we will get an F value for the interaction term. This F value is derived in a very similar way to how it was derived in our one-way and repeated measures ANOVAs. We find a sum of squares for each of the variables in the interaction for our between subjects variability. We find sum of squares for our within subjects variability. Each of them has the degrees of freedom, which we'll go over how we find those in a minute. We divide sum of squares by degrees of freedom to get a mean squared. And then we divide each mean squared by the within subjects mean squared to produce an F. Now, we're not actually going to learn the math here because, frankly, it's a lot. We don't need to learn how to do this math by hand. It's too much. Just understand that this factorial ANOVA, in this case, a two-way analysis of variance because we have two variables, is doing much of the same work as our previous ANOVAs, and that it's partitioning variance from between subjects variance to within subjects variance. And then each of our individual variables provides variance. And then the interaction between our two variables provides variance. And we'll end up with an F test statistic for each of those 3 effects. Okay, so let's do an example all the way through from marginal means all the way to an ANOVA table, and we'll see how our interpretation of marginal means sort of intersects with our ANOVA table and interpretation. So in this example, we're going to ask a question about how the age of students and their teacher expectations impact their IQ. So our means here in our cells of our Punnett square in our marginal means table are IQ scores. They're divided by 7-year-olds and 15-year-olds, and then by whether teachers had high expectations of that student or they had low expectations of that student. So each of our 4 numbers here represents an average of all the individuals that we would find within that cell, within that experimental group. So we have 7-year-olds whose teachers had high expectations, 7-year-olds whose teachers had low expectations, 15-year-olds whose teachers had high expectations, and 15-year-olds whose teachers had low expectations. So we're going to do the same thing we just did. We're going to take our marginal means across, and then we're going to take our difference scores, and we're going to interpret whether we have main effects or an interaction, and then we're going to look at how that will compare to an ANOVA table if someone were to actually run the statistics in SPSS on the computer. So what I want you to do right now is pause this video. I want you to calculate your marginal means for our main effects. I want you to calculate your different scores, then compare the differences between your different scores. And I want you to come to some just sort of general eyeball conclusions about whether you expect us to have a main effective age, whether you expect us to have a main effect of teacher expectations, and whether you expect there to be an interaction between age and teacher expectations. So go ahead and pause the video and then click play when you're done with that and you want to come back and look at the answers. So hit pause. And I hope you're back. So let's take a look at our marginal means. We average, let's start with age here. We average down, and we see that the average 7-year-old has an IQ of 107.5 in this example, and the average 15-year-old has an IQ of 110. Now, IQ is on a relatively large scale, right? IQs, normal IQs or IQs typical in the population, range anywhere from on the low end, we would consider 70 or 80, low IQ. On the high end, we would consider 130, 140 high IQ. So we have a fairly large range of scores here. We're not talking about a 1 to 10 scale. We're talking about a scale that goes from the high decades to the low 100s. So a difference of 2.5, right, 107.5 to 110, is not a very promising difference, right? It looks like 7-year-olds and 15-year-olds are pretty similar. I mean, 15-year-olds are a little higher, but on the scale of this measurement tool, probably not significantly higher. So I would not be confident in this main effect. They're a little higher, but probably not significantly higher. Now let's look at the main effect of teacher expectations. For students, regardless of age, right, we average our 7 and 15-year-olds together. Regardless of age, students with high teacher expectations have an IQ of 112.5, and students with low teacher expectations have an IQ of 105. So this is a little bit more of a difference, right? We're talking about 7.5. That looks like it might be something. We can't be sure. We don't have the statistical data yet. We don't have the ANOVA table and the F values to tell us what's significant. But this certainly looks more promising than our main effective age. So I would say that I would walk away from this means table with the expectation that I probably have a main effect of teacher expectation, and I probably do not have a main effect of age. Let's look at our different scores. If we subtract down the table, we take 115 from our 7-year-olds minus 100 gives us a difference of 15. 110 minus 110 for 15-year-olds gives us a difference of 0. So we have our different scores. Now we need to ask ourselves the question, is there a difference between our different scores? And I would say undeniably yes, right? 15 points of a difference is a big deal on this scale. So we look like we have an interaction. Let's dive in a little bit to this interaction, see if we can maybe interpret it. So all 15-year-olds have an average of 110, meaning teacher expectations don't matter for 15-year-olds IQ, right? If you have high expectations, you have a 110 IQ. If you have low expectations, you still have a 110 IQ. Doesn't matter. But it does matter for 7-year-olds. 7-year-olds who have high expectations from their teacher achieve a high IQ, right? They are much higher than the 7-year-olds whose teachers have low expectations of them who have a 100 IQ. So it looks like expectations matters for 7-year-olds, but teacher expectations do not matter for 15-year-olds, right? That's the essence of our interaction, that expectations or the effect of expectations depends upon your age. For 7-year-olds, expectations matter. For 15-year-olds, expectations look like they do not matter. So I would say we should be expecting a significant interaction between our two variables. So someone actually had real data on this. So let's look at their ANOVA table. Remember, we have three pieces of this ANOVA table that are going to really be important to us. For the time being, I want us to ignore this line that says corrected model, and I want us to ignore this line that says intercept. Just pretend like they don't exist. We don't need to worry about them right now. What we are interested in is our line for the main effect of age, our line for the main effect of teacher expectations, and our line for the age by expectation interaction. We can see that we get a sum of squares for each of these terms. We get a degrees of freedom for each of these terms. We get a mean square for each of these terms. And we get an F value for each of these terms, plus a significance value. So we're going to take each of these one at a time, and we're going to break down how we should interpret them. So the effective age, just like we suspected, isn't really there. We got this degrees of freedom of age by the number of levels minus 1. Right? So we had 2 levels of age minus 1 gives us 1 degree of freedom. We end up with a small f value, 1.125, which let's say our alpha, our significance cutoff is 0.05. So we're above that, so we are not significant. So age does not have a main effect on IQ. Let's move to teacher expectations. We similarly found the degrees of freedom from teacher expectations by taking the number of levels minus 1. So there were high expectations and low expectations. So 2 minus 1 is 1 degree of freedom for teacher expectations. They have a much larger F value of 10.125, which produces a small significance value of 0.003 or p-value. This significance value is below our threshold of 0.05. Because it's below our threshold of 0.05, we reject the null and we conclude that the effect of expectation is statistically significant, just like we thought it would be. So it looks like for students, regardless of age, high teacher expectations means higher IQ, low teacher expectations means lower IQ. Right? Remember, this is a main effect, so expectations regardless of age. And lastly, our interaction appears to be significant. We got this degrees of freedom by taking our number of variables minus 1, so 1. And then we have again a large F value. These are the same number, 10.125, 10.125. That's just some randomness there. That will not necessarily happen or will rarely happen. We have a significance value of 0.003. It's also below our threshold of alpha of 0.05. So just as we suspected from our means table, we have a significant age by expectation interaction such that teacher expectations matter for 7-year-olds, but teacher expectations do not matter for 15-year-olds. Okay. So here we have a little summary of each of our interpretations. Again, we have a significant that says man effect. That should in fact be main effect of teacher expectation, which means that regardless of age, teacher expectations impacted IQ, and the direction of that effect was such that high expectations led to higher IQ. There was no main effect for age, right? We did not find a significant main effect of age, which suggests that IQ does not differ across age, which is actually the way that IQ works. And our interaction was significant, right? We found a significant interaction effect where 7-year-olds' IQ scores were, in fact, impacted by teacher expectations, right? The IQ scores of 7-year-olds depended upon teacher expectations, but the IQ scores of 15-year-olds did not depend upon teacher expectations. So the effect of teacher expectation depended upon the age of the student. So that is a close on our section 3 for marginal means tables and ANOVA tables for factorial ANOVA. In section 4, we will work on continuing to interpret these main effects and interactions, but looking at them from the perspective of a bar graph, sort of visualizing them aside from our marginal means tables. And you'll find, as I find, that the ability to visualize these is really helpful in interpreting particularly the interaction. So that's what we're going to spend a lot of time of focusing on in section 4. So thanks for listening. Check out section 4 when you have the chance, and I will talk to you later.